In this brief presentation, I will be talking about the importance of high-performance computing in computational data science. Before seeing about the HPC, let us see the importance of what is computational data science and its application. The research in computational data science is done in cycle. For instance, we consider some specific industrial application or scientific application or even the business problems, and we make some assumptions and simplification to the considered problem, and then we derive a mathematical model with all these assumptions and so on, or a network model in data science. And then we solve these mathematical models by a numerical scheme or the algorithms of ML AI type. When we talk about the algorithms, of course, we need to implement in a computer. And when you implement in a computer, we are talking about the supercomputers, not general purpose computers. So once you get the solutions from the supercomputers, then you have to validate and verify the uptime results. Once the validation and verification is over, then what we really need is we need to perform the production run. Once we get the data from the production run, we derive conclusions or we apply some data-driven models to get insights from the big data that we are getting. In case the solution that we have obtained from these computations are as expected, then we can exit from the cycle, or otherwise we might have made very strong assumptions on the simplification. So we have to relax the assumption, and in turn we will get a very complex model. When you have the complex model, obviously the numerical scheme should be robust and as well as the complex enough to handle the complex problems. Then obviously the algorithms need to be modified and you will get a better results hopefully, and then you continue the cycle or exit the cycle, depends on whether you are reached the attention or not. So that's the computational science. And if you look at the computational science, you really need an expertise from maths, physics, and computer science and domain specific knowledge. So you need to be good at it. So with this, let us see what is computational data science, where it is applied. The computational data science is used when the experiments are too large or too expensive or too dangerous, and useful in what-if studies. For example, we do not want to crash the car every time, or maybe 100 times, in order to get a meaningful outcome. Instead, we can do the simulations and apply data-driven models, and then maybe one or two simulations, one or two experiments with further comparisons and so on. And this will in turn save huge cost in terms of the production. So computational data science is a powerful modern tool for scientific investigation, and it is a product that can be used in a product design and the process development and manufacture. So when you talk about the applications, the first application comes to your mind is the application in aerospace, but not necessarily the aerospace application. It can also be applied in ship hydrodynamics, multi-phase simulation. Wherever you have the computational CFD applications, you can apply the computational data science. The other application that comes to our mind is the weather prediction. The weather forecasting is one of the very, very challenging and also the really very large scale problem. And even with the present day computers, we are able to simulate with the resolution of few kilometers, if not meters. So this shows the complexity and as well as the size of the problem and the necessity of the supercomputers. So not only these applications, so you can apply the computational data science to any industrial applications, or even in the medical field. Health sector is one of the big push that is getting from the computational data science. And even the galaxy formation, or even if you want to study the planetary movements, if you want to study the climate change modeling, or even the traffic flow simulations, extreme weather predictions, or even in the molecular dynamics simulations, to the microscopic level or the atomic level simulations, or even in movies. So these are some of the applications. Of course, if you want, there is no limit into it. Of course, whatever I have covered is not the complete list of applications where the computational data science is applied. Then the question is, when you talk about these type of large scale applications, what we really need is we really need a supercomputer. Now the question comes, what is supercomputer? In a layman's language, supercomputer is a computer with many CPUs and GPUs, maybe even with other accelerators. And compared to the general purpose computer, the supercomputer will have a high level of computational capacity, and usually the supercomputer's performance is measured in terms of flops, that is, floating point operations. When we talk about the flops, we are talking about the teraflops and petaflops for the measurements in supercomputers. If you look at the top three supercomputers as of November 2020, the top three are, the first one is from Japan and the next two are from US. If you look at the performance of the peak performance of the top system, it's in the 442 petaflop, whereas the next one is three times less, more or less about 148 petaflop. That's the, and then the 94.6 petaflop is the third system's performance. The supercomputers in India are these three are the within the top 500. For example, the Param Siddhi is the recent entry from the CDAC. That machine is ranked at 62 in the top and all over the world, which is having around 41,000 core CPUs and a peak performance of 5.2 K teraflops. So in terms of the projections, what we can see is it is in around 90s. It has started with some gigaflops from the peak performance. Now, if you look at in the 2020s, we are talking about a few hundreds of petaflop. Maybe in future, maybe another 4 or 5 years, we can expect an exascale machine. In terms of the contribution or system share from country-wise, if you look at the China, of course, is having a more share, and the next is United States, followed by Japan, and so on. In terms of the performance share, of course, it is dominated by the US, and then the Japan, and then the China. Unfortunately, we don't see the share or the color from India because we do not have a significant contributions. But hopefully, with the recent initiatives, supercomputer missions, and the initiatives by the CDAC, this gap will get filled. And in addition to all these statistical data, so you can also go to the top 500. That's where I got all these pictures, and you get more information about all the supercomputers and as well as the latest news. So what is really necessary in order to fill the gap? What we really need is, if you look at the top of supercomputers, all supercomputers are with CPUs, and when you talk about the CPUs, it's a multi-threaded CPUs. We talk about the nodes. So nodes, multi-threaded CPUs, and then we talk about the accelerators like GPU cards. So when you talk about the algorithms for these type of heterogeneous systems, what we really need is we really need an hardware-aware numerics, which means the numerical scheme, whatever that you are using, or the algorithm that you are using, should aware that the system is having a heterogeneous configuration starting from different nodes, and each node might be having several threads or several CPUs and several cores. And also, in addition to that, each node will be having an array of GPUs or even other accelerators. So your numerical scheme should be able to use all these hardwares and then makes the computation faster. At the same time, the biggest bottleneck of any HPC algorithm is scalability, which means that your communication should be minimal, so that you can get a better scalability. You can use the entire capacity of the supercomputers. The scalability, when you talk about, again, the people talk about, okay, how big the data is, how small the data is. When you want to reduce the data size, obviously the recent trend is about using a reduced precision. When you talk about the reduced precision, it need not be all computations with a reduced precision. We talk about the mixed precision, maybe some computations with a double precision, some computations with half precision, or even the single precision. So several possibilities in terms of increasing the scalabilities, and once the bottleneck of scalability and the load balancing, all these things are taken care, then I do not see the reason why the developed algorithms will not be able to harness the supercomputer. Okay, that's all I want to convey. Thank you.